Welcome students, this is Ravi Shankar. In our last video, we have studied about the dielectrics. While studying about the dielectrics, called to be the polar dielectric and non-polar dielectric, we have stated or we have explained about the polar molecules and non-polar molecules. When a polar dielectric as well as a non-polar dielectric are placed inside an external electrical field, the dipole moments are either induced or they are aligned in a particular direction. Generally, we called them as polarization. So today we are going to consider about that topic called to be polarization. What do you mean by this polarization? See, let us consider in general. When you are considering in general, polarization is a phenomenon. We can say polarization is a phenomenon, is a property. So we can say polarization is a phenomenon of arranging or aligning either the permanent electrical dipole moments, or permanent dipole moments or the induced dipole moments either the permanent dipole moments or the induced dipole moments is arranged in the direction of the electrical field. See the phenomenon of aligning either the permanent dipole moment or the induced dipole moments in the direction of the applied external electrical field, In general, we can consider like this. That is, the polarization is a phenomenon of or property of arranging or aligning either the permanent dipole moments or the induced dipole moments in the direction of the applied external electrical field. But technically, we are in your book, the explanation was being given in terms of dipole moment per unit volume. Also, we can define as this is the thing given in your book. Also, we can write polarization is defined as the total dipole moment, per unit volume, arranged per unit volume is also considered to be polarization, volume of the dielectric. This is a technical explanation or a technical definition, and this is a common way using the property. So both are correct, but the second one is given in your book. So in general, polarization is a phenomenon of aligning either the permanent dipole moments or the induced dipole moments in the same direction as that of the applied external field. Technically, we can define it out as polarization is defined as the total dipole moment per unit volume of the dielectric. And it was found out that the amount of polarization cost, we can say, the amount of polarization cost. So the amount of polarization is directly proportional to that of the applied external electrical field. if more and more amount of electrical field is applied, more and more amount of dipole moments are aligned in the same direction. So I can say like this: the dipole moments that are being aligned, generally called to be P vector, is found to be directly proportional to that of the applied external electrical field, E external. See, when you are removing this proportionality, I can write P vector is equal to a new concept or a constant is introduced, represented by this symbol psi of E, psi of electrical field. It is called to be susceptibility of electrical field, multiplied it with E external. This we are calling or considering it as the expression for polarization, where here we have introduced a constant psi of E. This we are calling it out as a constant. This quantity is a constant, and the constant is called to be, here E is represented for electric. So electric susceptibility. Electric susceptibility. What do you mean by this? It is a character of the dielectric susceptibility, which is one of the character of dielectric. The susceptibility, we will be studying it in detail while studying about the third lesson. Okay, so this we are calling it out as this phenomenon, we are considering it as polarization. What is the next concept that we have to go? The next topic that we have to study is how electrical field is induced inside a dielectric. So that was given as a next topic 1.715. In that 1.715, the topic number in your book, the topic number is considered to be 1.715. So the topic number we can write it out as 1.7.5. Generally, what will happen if an dielectric is placed inside an uniform electrical field? So the topic was being given that induced electric field inside a dielectric. That was the topic given. Let us explain. What do you mean by this? See, before studying this, let us recall what you have studied in case of a conductor. So, first of all, what I am going to consider is, I am considering a conductor. So, this is a conductor. See, this conductor is placed in between the parallel plates of a capacitor so that an uniform electrical field E is applied, having positive charges on one plate and negative charges on the other plate. So when you are considering an uniform electrical field with the help of this capacitor, and inside this if you are placing an conductor, then electrons from this end of the conductor will reach the other side. This we have already studied. And here on the other side you will be having equal number of positive charges. So this E is E external, acting from left to right. But when this conductor is placed inside this external uniform electrical field, inside this conductor you will be having an electrical field generally called to be E internal. This E internal will be developed till that E internal is equal to that of E external. Already we have studied in the property of the equilibrium of conductors. So, static equilibrium of conductors. So, we can write what is the net value. Electrical field E net is equal to, we can say like this, E net is equal to E external electrical field minus E internal electrical field. See, when you are considering conductor, I can write in case of a conductor, I can write, isn't it? In case of a conductor, electrical field available, net electrical field available is equal to 0, since E external is equal to E internal and also in opposite side direction. So E external is equal, I can write minus of E internal. This we have already studied in the previous case of conductor in electrostatic equilibrium. If you want, we can write this in technical or write this in words. See, in case of conductors, we can say when external electrical field is applied, what will happen when we are applying an external electrical field? Then we can say the internal electrical field is developed, then an internal electrical field is developed which is equal and opposite to external field, which is equal and opposite to what? Equal and opposite to external field. Equal and opposite to external field, and so the conductor is in electrostatic equilibrium, and so the conductor is in electrostatic equilibrium. That we have already studied. See, here it is not needed, but in order to study a dielectric to be placed inside an external electrical field, we have explained what will happen in case of conductors. Similarly, we have to see what will happen if an dielectric is placed inside an external electrical field. So let us consider the next one. What is the next one? But let us consider the case of, but in case of dielectric. But in case of what? But in case of dielectric. What will happen in case of dielectric? See, let us take like this. I am considering an dielectric. So this I am considering it as dielectric. If you are considering an dielectric, there are no free electrons. All the electrons are considered to be bound. Now, when this dielectric is placed inside the plates of a capacitor, that is, at one of the plate you are having the positive charge, and at the other plate we are having the negative charge. So when you are applying an uniform external electrical field, what will happen? That is what we are going to study here. So when I am applying an external electrical field inside this dielectric, the external electrical field will realign the charges that is available here, and there is, in case of that dielectric, since there is no free electrons, this is happening. So the charges now develop an internal electrical field, but in the opposite side direction, which will be less than that of external electrical field. Okay, what will happen? Let us write it here. See, in case of dielectric, see, the internal electrical field won't get developed as in conductor because there is no free electron. So in case of dielectric, we can write like this: as there are, or we can write as there are no free electrons, as there are no free electrons, as there are no free electrons, what will happen? The external electrical field just redistributes, realigns the electrons. Here the electrons means the bound electrons, or we can say realigns the charges, so that in such a way that, or we can write in such a way that an internal electrical field is developed. An internal electric field is developed. An internal electrical field is developed. So, if you are considering this internal electrical field developed will be always less than that of the external electrical field. See, what will happen to this internal electric field? See, we can consider a point. What point we can consider? But we can say, but the magnitude of internal electrical field. But the magnitude of internal electric field. What is that magnitude? Let us write like this: modulus of E internal. So, this magnitude of E internal electrical field is always less than that of the magnitude of the external electrical field applied. Okay, so what is that net? Therefore, since the internal electrical field is less than that of external electrical field, we can say E net electrical field is not equal to what? Is not equal to 0. Since E, we have studied a formula, E net vector is equal to E external electrical field minus E internal electrical field. So, we can say the E net is in the same direction as that of the external electrical field. Therefore, we can also say E net electrical field, E net is in the same direction, or we can write in the direction of external electric field. In the direction of external electric field. Are you able to understand? See, we have considered two cases. One is the conductor, where we can say the applied external electrical field will make the internal electrical field, where the external electrical field and internal electrical field are 0, and there is a net electrical field is equal to 0. So, inside a conductor, there is an electrostatic equilibrium. But when you are considering an dielectric, since there is no free electrons inside the dielectric, due to the application of the external electrical field, the charges are aligning in such a way that an internal electrical field is developed. But the developed internal electrical field is having its magnitude less than that of the magnitude of the external electrical field. So, we can say that net electrical field is not equal to 0. Since net electrical field is given by the formula E external minus E internal. Since E internal is less than that of E external, E net is not equal to 0. Moreover, E net is in the same direction as that of what? Is in the same direction as that of the external electrical field. See, in your book they have given two examples to illustrate this. How you can illustrate. So, two examples are being given in order to illustrate. The first one is, consider an rectangular dielectric slab placed between two oppositively charged plates. See, simple. What is the illustration 1? Let us consider like this. See, let us take the illustration as 1. Okay. Let us consider the illustration 1. What I have explained in the previous cases again written. You consider an dielectric. Okay. Inside this dielectric, you are having no free electrons. This dielectric is placed in between the plates of an parallel plate capacitor, so that the plates which are having the positive charge on one side and the negative charge on other side will be developing an uniform electrical field. E vector. Generally, we are calling it out as E external. Now, when you are considering this dielectric, this is called to be dielectric, then what will happen? The electrons will be, or the charges will be aligned inside what? Aligned inside this dielectric in such a way that on the nearer side of the positive you will be having negative charge, and this is the positive charge. On nearer to that of the negative plate, you will be having the positive charge, and the other side you will be having the negative charge. So the charges are being aligned. Okay. When that uniform external electrical field is applied, it polarizes the dielectric. So, okay. So I can write, when this external uniform electric field is applied to a dielectric, what happens? The charges are aligning in a definite direction. That is, dielectric polarization is caused on the dielectric. So, we can say dielectric is applied to dielectric, polarization is caused. Polarization is caused. Or we can say like this. See, when an external electrical field is applied, that external electrical field polarizes the dielectric which is placed in between what? Which placed in between the two plates. So what is that polarization is caused? See, induced negative charges are available near the positively charged plate, and induced positive charges are available nearer to that of the negatively charged plates inside. Okay, but inside the dielectric, the net charge is 0 even in a small volume. See, we have told that the dielectric is said to get polarized, so that at the nearer end of the positive charges you are having negative charge, and nearer end of the negative plate you are having the induced positive charges. But inside the dielectric, an important point, but we can say, inside the dielectric, the net charge is always equal to 0. Net charge is equal to 0 even in what? Even in a small volume. This we are calling it out as an first illustration. See, when you are having the dielectric in the external field, then we can say the surface charge densities on the two sides are equal. One as plus sigma b and another one as minus sigma b. The charges are called to be bound charges. What do you mean by this? What I have told now. See, when you are considering the induced charges in this dielectric, due to this external electrical field, here you will be having what? Here you will be having this dipoles to be arranged. Here also, in such a way that at the nearer end of the positive plate you will be having the minus charges, and nearer end of the negative plate you will be having the positive charges, generally called to be induced charges. When you are considering the surface charge density at this end, you will be having minus sigma. It was being given in your book as minus sigma b. Similarly, on this side you will be having plus sigma b. So, where sigma we are calling it out as surface charge density. See, these charges won't move inside the dielectric. So, these charges are considered to be bound charges since the induced charges, are not in motion, we can say since the induced charges are not in motion, these charges are called as what charges? Bound charges. They are taken to be bound charges. So this, let us consider it as one of the demonstration. What is the demonstration? Here we have placed a dielectric in between the parallel plate capacitor where an external uniform electrical field is applied. So because of that, what happened? Because of that, inside the dielectric you are having the bound charges. The charges never move, but the charges are made to align in one particular direction. So we can say the dielectric is said to be polarized when it is placed inside an external electrical field. But when you are considering the net amount of charges inside this dielectric, it is equal to 0, even though if you are considering a small volume. When you are considering the charges available at the edges, the surface charge density is considered to be plus sigma b and minus sigma b. These charges won't move. These charges are called to be induced charges. Since these charges won't move, the charges are called to be bound charges. This is one of the illustration. We can consider one more illustration and practical illustration. What is the practical illustration that we can consider? So let us consider illustration 2. So I am writing here illustration 2. What do you mean by this illustration, or how we can explain this? See, you consider a balloon. That balloon, when it is rubbed against any material, will get charged. Then it can able to stick on to what? Then it can able to stick on to the wall of, or stick on to the wall. What is the reason? So generally we will be saying like this: consider a charged balloon. So consider a charged balloon. See how a balloon can be charged. Let us consider this is the balloon, and here I am having the here I am having the wall. Okay, consider a charged balloon. So I can consider a charged balloon. When you are considering a charged balloon, taking the balloon like this, and a wall here. So this is a wall, and this we are considering it as a balloon. Now the balloon is charged. Let us consider the balloon is said to have positive charges. How you can say that the balloon is said to have positive charge? Or usually when the balloon is rubbed, it will be getting the negatively charges. So let us consider the balloon is having negative charges. Okay. See, let us take like this. The balloon, when you are considering the balloon and rub it with the help of a dry cloth, the balloon acquires a negative charge, not the positive charge. Balloon acquires a negative charge. Take the balloon and bring it nearer to that of the wall. What will happen? The balloon will stick on to the wall. Why? The balloon stick on to wall. Why? Balloon sticking or stick on to wall. So it is sticking on to wall means why it is sticking on to wall. That is what we are going to see now. So you consider a charged balloon. The charged balloon after rubbing stick on to the wall. What is the reason? So the reason is the negatively charged balloon. Okay, why it is sticking on? The reason for sticking is the negatively charged balloon when brought near the wall. The negatively charged balloon negatively charged balloon when brought near the wall, it polarizes, or we can say it produces an opposite charge on the surface of the wall, and we can able to get the ball to be attracted. See the wall, it polarizes, nothing but it induces opposite charge, or the balloon is negatively charged, means the wall is induced with what? The wall is induced with the positive charges. Polarizes or induces opposite charges on the surface of the wall. Okay, opposite charges on the surface of the wall. Since it induces opposite charges on the surface of the wall, the balloon sticks. The balloon is sticking onto what? The balloon is sticking onto wall. The balloon is sticking on to wall. This we are calling or considering it as the illustration. So, in both of the cases, we have considered that when you are taking that illustration, that is in first illustration as well as in the second illustration, when an external electrical field is applied. In the first illustration, when the external electrical field is applied, it polarizes the dielectric. Then in the second illustration, when the charged balloon after rubbing, when it is taken nearer to that of the wall, it polarizes or induces the charges in the wall. Because of it, the balloon can able to stick on to what? The balloon can able to stick on to the wall. This is considered to be the second illustration. So this we are explaining it as induced electrical field inside what? Inside the dielectric. Now, what do you mean by dielectric strength? The next concept we are going to state is dielectric strength. What do you mean by dielectric strength? See, the name itself is self-explanatory. The strength of electrical field inside the dielectric. How you can able to get the strength of the electrical field inside the dielectric? See, what we have studied. We have already studied that if an external electrical field is applied to a dielectric, then it what happens? It polarizes or it induces. The charges are getting aligned. If the applied electrical field is strong, what will happen? If the applied electrical field is more than enough or very high or very strong, automatically the bound electrons, that is, we are calling it out as the electrons which are being bound to the atoms, that bound electrons will tear up from the atoms and the charges will move apart so that they can able to conduct. If so, we can call that as dielectric breakdown. Clear? See, I will be saying, if the applied external electrical field, if the applied external electrical field is so strong then the atoms will tear apart from the dielectric. If they are so strong or highly strong, then we can say the atoms will get tear up from dielectric so that the bound charges become free charges. Become free charges. Clear? See, in a dielectric you are not having any free charges, you are having only bound charges. But when the applied electrical field is considered to be so strong, then that strong electrical field will break up or tear up the atoms from the dielectric, so that the bound charges become free charges. So this phenomenon is called, or this is called as dielectric breakdown. This is called as dielectric breakdown. This is taken to be, or this is called to be dielectric breakdown. So now we are going to say what is dielectric strength. What does dielectric strength means? See, before breaking down, how much amount of electrical field can be withstand by that dielectric. Okay, before breakdown, the maximum amount of electrical field that can be applied to a dielectric is called to be dielectric strength. Are you able to understand? See, the maximum amount of electrical field, the maximum amount of electrical field, maximum amount of electric field, or we can say external electric field. So the external electrical field applied so that the dielectric can withstand, or we can write the dielectric can withstand before it gets broken down. Before it gets broken down is called as dielectric strength. Is called as dielectric strength. So what is meant by this? Dielectric strength is nothing but the maximum amount of electrical field that can be applied to a dielectric so that the dielectric won't get what? So that the dielectric won't get free charges, or the dielectric won't get broke down, or it breaks down. See, let us see some numerical values. For example, let us consider air. Air is an dielectric. So I can write some of the examples. I can write like this. Datas. See, dielectric of air. Dielectric of air, because air is an dielectric. Okay, I am writing like this. Dielectric strength of air. Dielectric strength of air is 3 into 10 to the power of 6 volt per meter. See, if an electrical field is more than this value, what do you mean by this? If the applied electrical field is, more than this value, okay, applied electrical field is more than this value for air, then the air medium can produce what charges? Free charges, and it can able to conduct. So, and theory part, what we have studied it in this video, started from polarization. After that, induced electrical field inside the dielectric. For that, we have gone with 2 illustrations, and from that we have gone with another definition called to be dielectric strength. Hope you should have understood. Go through this again and again and study it thoroughly. Thank you.